Alright, today we're going to integrate functions that look like this, which are more complicated than what we've done. Now, one option is to raise this to the fifth power. So multiply that by itself 5 times. Then multiply this through with the distributive property to create this nice power function that's this long, with the 23rd power being the highest power on it. We'll call that option A, which is not a good option. Option B is to use the substitution technique of integration. And that's the yellow sheet I've given you. The substitution method, number 1 says, what type of function are you integrating? Now, this is the key to the problem. Okay? The type of function is going to be a trig function or a power function. That's what we know how to integrate at this point. Trig functions and power functions. Okay? And if we take a look, when I'm looking at this problem, I don't look at the whole problem. I look at the part that looks like something I can work with. And what I can work with is, that is something to a power. And get used to the word something, that's what you want to be saying when you do this. It doesn't matter what's in that parentheses. It's something being raised to a power. That makes it a power type of function. Right? I have a power rule of integration. So the whole idea of substitution method is we're going to rewrite this integral into an easier form. We're going to make a really simple integral out of this. Okay? And I don't have to use the entire function. I just have to use parts of it. So this is something to a power, so it's a power function. Step 2. What is the argument of this function? Okay? If it's a power function, what's being raised to the power is the argument. So the argument of this function is 3x to the 4th minus 7. Right? So whatever's being raised to power. If it said sine of 2x, 2x is the argument of a sine function. So it's a sine function, argument is 2x. So that's the first 2 parts of this are very important to the process. Okay, so what I want to do is, whatever the argument is, I want to call that u. U equals 3x to the 4th minus 7. You can call it something else if you want to, but the technique we're using is called u-substitution. So I'm going to use the letter u. Every calculus book I've ever seen calls it u-substitution. I don't know why u is so important, but that's what they use. I'll use it. Maybe because u is almost never used. So this is its time to shine. But that's what's happening here. U equals whatever the argument is. And then I want to find the differential. If you recall differentials, differentiate each term and put d, whatever that letter is, next to it. So the derivative of u is 1 du. The derivative of 3x to the 4th is 12x cubed dx. Derivative of negative 7 is 0. Now, ideally, what just happened here is that whatever du is lives in the function. So if we take a look here, here's du. Forget about the 1. That was bigger than I expected to be. All right. Du is 12x cubed dx. And notice, 12x cubed dx lives in the function. Right? So the whole idea of u-substitution goes like this. That's my problem, right? I've got an integral symbol, and I've got this argument to the 5th power. That argument is u. So that's u to the 5th power, right? And this stuff underlined in purple, 12x dx, is du. That integral is the same problem as this, because we've identified what u and du are. So we do a u-substitution. And this integral is really easy to do, right? The antiderivative of u to the 5th power, du, is going to be u to the 6th power over 6. I'm going to put a plus c. I'm putting plus c because there's no interval here, so it's an indefinite integral is what it's called. I don't know if we've actually seen an indefinite integral yet, but what we've seen so far mostly has been numerical ones. Here are definite integrals, right? Where we have to evaluate, the c's go away. Well, if you have an indefinite integral, the c doesn't go away, so you put the plus c there. And then the final step is, once we get the antiderivative of this thing, now I want to put u back into the function. So this is the answer, but I don't want u in the answer, I want x in the answer. So u is 3x to the 4th minus 7. That's being raised to the 6th power over 6 plus c. There's my antiderivative, or my indefinite integral, if you will. basically what we're doing here is we're undoing the chain rule. If I was to differentiate this function, this is a chain rule situation, right? I do 6 times 1/6 is 1, 3x to the 4th minus 7 to the 5th, times the derivative of the inside, 12x cubed dx. We're extracting the inside, finding its derivative, and seeing that its derivative is part of the expression to begin with, and then we're just extracting that in that manner. So du is right there, u to the 5th is right there. We create a nice simple integral, we do it, then we substitute back in. And when it works nicely, all is well. Makes our life great, and we can be happy about how wonderful these things are. So hopefully they'll be like this all the time.